And if y'all have questions, ask them loudly because it's hard to hear on that thing. You can hear me, but...
What page of the notes are we on?
Page of the notes. These don't have a specific page, pre-printed page number, but it's after the organic. It says student lab 1 of 3, the nuclear chemistry one. So we are doing nuclear chemistry in a day. This makes up a very, very small percentage of the AP exam, so we don't have to spend a lot of time on it. You spend way more time in pre-AP than we're spending on this. It's going to be super fast, wham bam, to the point. And I'm giving you the minimum of what you need to know, all right? You might see 2 questions on the AP if you're lucky, all right? And if you're good, you get a demo life lesson story at the end of the period, which is actually related to the topic, so double bonus, all right?
Don't stand near a nuclear bomb.
That would be a life lesson, yes, you're correct. Do not stand near nuclear bombs. And don't go to Japan right now.
Are you saying that you're the result of nuclear radiation?
I am that radioactive, yes.
Dr. Devo.
Okay, back on topic. It's really not funny if they don't see your face.
So. It's even funnier if they don't see my face.
Because your face is funny.
Your mom is funny.
Mama Demo's pretty awesome. All right. So looking at the beginning, real quick, when I say nuclear radiation or I say nuclear stability, what are some things that come to your mind?
Uranium.
Uranium, that's a very popular nuclear. Plutonium. Okay, let's not name every element on the chart. What other things do you think about?
Japan.
Japan,
Iodine and
Fission.
Fission.
Okay, she's got hot.
Hydrogen. Bomb.
Me and my mom's obsessed with salt.
North Korea.
That's right.
You guys are just a bunch of nerds.
Iran.
I'm not.
Iran.
I already said that.
Okay, so you all tend to go toward the destructive side of like
Kim Jong-il, 3
bomb.
Mile Island, Chernobyl.
Baker test.
Avi's hair.
Alright. I was kind of leaning, hoping for some things like half-life, alpha, gamma, that kind of thing. I heard gamma, but no, you didn't go there. Okay. So you all have some preconceived notions about nuclear chemistry, or as Bush says, nuclear chemistry. But I hope that they're all correct, and we'll see how much you guys really know. To start with, there are some rules of thumb about stability of nuclei. For small bitty atoms, if you have the same number of protons and neutrons, it's probably going to be pretty stable. I don't know if y'all remember in middle school, they might have taught you that certain atoms have the same number of protons as neutrons, and that's actually not true. The most stable ones do, but that's one of those rules of thumb. As the atoms get larger, you're going to want to have more protons than more neutrons than protons, and when you do, you have a more stable region. What you need to know is pretty much anything, it says beyond bismuth, but bismuth has quite a few radioactive isotopes, so anything bismuth and beyond are going to be your less stable isotopes. So anything beyond that on the periodic table is going to be radioactive, okay? So you're going to be balancing these transmutation reactions. You've seen them before. Transmutation, that's just the name of these little things that you did in pre-AP where you just added up protons and neutrons and balanced them. Yeah?
So the lanthanides are not radioactive and the actinides are? Or?
Yeah, well, there's really no lanthanides that I've ever seen in use in any sort of radioactive. Now, whether that's not true or not, I have a hard time believing none of them are, but they're just not commonly used.
Okay.
But we obviously know the actinides are. So. Okay. Types of radiation you guys have to know. You have to know alpha radiation. Alpha particles are helium nuclei. Okay, 4/2. It is a helium nuclei. You can either write the word He or you can actually draw a little Jesus fish. Either one is fine. And what it represents is the top number is protons and neutrons, the bottom number is just protons. So you already know that from normal condensed stuff we did with elements like the first day of chemistry. So the way these work, if you're told that uranium undergoes alpha decay, you take your uranium, you pull out an alpha, and then you add up. What numbers do you add to 4 to get 238? Ah, 234. What do you add to 2 to get 92? Oh, 90. Which one of these identifies the element, 90 or 234? 90. So you find 90, and what is that? You look, find 90, and then you'll find TH, which is How about thorium? Not thallium, thorium. Okay. So, alpha emission is your least dangerous emission. Down here it talks about how skin can stop it. What else? Paper. They often use paper and things like that to stop it. Easy stuff, not too dangerous. You need to know beta emission, also known as an electron. Beta is an electron, and it is indicated with 0/-1. You got to know these by heart. If I'm at any point not on that screen, you've got to tell me because people at home can't see it, and that would be bad. And these can actually penetrate into your tissue. However, beta radiation is often used in radioactive tracers. Whenever we talk about barium enemas, that's a nice word, any sort of tracers they use on the gastrointestinal tract. I had a tracer once. This is not the Life Lesson by Demo story, but I was having gallbladder issues since I was a little kid, and they put thorium in me, which was, no, thallium I actually had, and it was really cool because they inject it, and then on the screen I all of a sudden saw my gallbladder like pop up. Kind of like that Willy Wonka particle thing, you know what I'm talking about?
Kind of like
the TV transfer one? You know?
Yeah.
Yeah, that's what it looked like. And then they injected me with this hormone that is what normally makes your gallbladder contract, and my gallbladder just kind of shivered. It didn't really work, so it never worked. It hasn't worked since, so we took it out. It was a good time. But anyway, the point is, they use these types of radioactive tracers, and all of them have beta emission. But we're talking about micrograms of the stuff, so we can handle it. We're tough. The one that we need to be concerned with the most, and when you hear nuclear fallout, and you think about like zombies, people who got hit with radiation, their arms are falling off and stuff, this is the radiation, gamma radiation. It's not particulate at all. It's 100% high energy. 0/0. That's it. So when you put these in a transmutation reaction, you're just chunking them on the end as products. They're not even part of the overall reaction. Next page. You've got to know positron emission, also known as proton. It is pretty much an anti-electron. It's the opposite of a beta. You guys need to know that. Pretty much the same energy as a beta particle. And then those are the four. So those are what you're responsible for. You need to know them by heart in order to do the problem. So a typical problem would be like alpha, uranium undergoes 2 alpha and 1 beta emission. What's your final daughter product? So you have to go through all that and do it. And we'll practice. You okay, Lindsay?
What?
You seem very, very depressed and sad.
Oh no. Shoot.
She's just.
I was thinking about something, then I forgot.
Because she had a bad
I
experience.
legitimately-
What did you have to drink at lunch? Just curious.
It might have been the milk I randomly found. It was close though.
Alrighty, quickly moving on, because I want to get to story time and problem solving here. We're going to have to revisit kinetics. You've already learned kinetics, but what connection between kinetics, I can't spell, between kinetics, and nuclear chemistry did I make even back then? What did I tell you about nuclear reactions?
It's like the electron going in and knocking the other stuff out, like knocking more stuff out.
Yeah, but you actually said what I was going for. Can you say it louder?
First order.
All nuclear reactions are first order. So we have to revisit first order kinetics. All right? First thing we need to revisit is what half-life equation, the half-life equation is. You have got to know that half-life equation because you won't be able to get through these problems without it. Where it came from was that first order integrated rate law. This wacky handout here, you're going to see so many mistakes I'm going to point out to you. These people are kind of weird. I don't like the way they do the first order integrated rate law, so we're going to go back to how we did it before. Ln of A minus Ln of A naught is equal to what? Y'all remember? Oh, no. The AP is just around the corner. Negative KT. You know it, you're just not talking. All right. So this is the integrated rate law. And then do you remember how we went from the integrated rate law to the half-life equation? What did we assume? Loud.
A is half of A naught.
Yes, we made A equal to half of the A naught, the original, and then we substituted everywhere we saw A naught, everywhere we saw A, we put 1/2 A naught in there, condensed it, and we came up with this equation. You're going to need to know both of these, all right? And this is an example of how we can get this working. If you want to cross through this, I'm not a fan of this particular one. And they end up doing it in this one weird way, and our answer is going to be rounded a bit differently, but ultimately the answer is going to be the same. So we have carbon-14. Carbon-14 can only be used on dating, can only be dating live things, right? So carbon-14 has a half-life of 5,720 years. That's a little bit of a half-life. Just a smidge.
Geological.
Yes, in the big picture of time, it's not. We are nothing in real time. We're babies.
We made up time, so yes,
Okay, that's a little deep. All right. So what we're going to do here is start looking at the integrated rate law for first order. ln of A minus ln of A naught is equal to negative KT. The question is, how old? That's time.
You need to scoot it over a little bit.
Oh, thank you. Thanks, Courtney.
You're welcome.
Courtney's.
Everyone on the internet's gonna think my name's Courtney now.
Go ahead and say
You sound
who you
like-
I'm Alex.
No, that's Courtney.
No, that's Courtney.
Nope.
Courtney.
He likes long walks on the beach. All right, so T is time, and so that's the age. We're going from 100% carbon-14 to all of a sudden we only have 60% left. So what can we do with those percents? Pretend they're 100, pretend they're, what's, not moles, grams, right? We're going to pretend these are grams, and we're going to assume we started with 100 grams, and at the end of the day we ended up with 60 grams. So we want to know, hey, how long does it take for that to decay that much, for this carbon-14? So what was A?
60.
No, 60. A naught's the original. This is 100, but what am I missing?
K.
I need K, so hold on. What can I do to find K? That's why I was saying we need the half-life equation. So I'm going to scoot over, we're going to lose this for a second, and I'm going to plug this into my half-life. T1/2 is equal to 0.693 over K. Do I have a half-life? Sure I do. It's that little bitty smidge in geologic time, according to a ring. And that's 0.693 over K. So y'all solve for K. We got to remember how to find units on this stuff, too. What do y'all get? I got, for time's sake, 1.21 times 10 to the negative 4th. Can somebody verify that? That is correct. Okay. And it's, what's my unit on this? Years? Years negative 1. Remember, let's review. I'm going to write down here, little review. Review of units. It's always 1 over your unit of time, which is years in this case, times molarity raised to the what for K's and kinetics?
M-1.
Yeah, molarity, not M minus 1.
And
The order minus 1, right? So if these are first order, 1 minus 1 is 0. So m to the 0, that goes away, so it leaves us with years to the negative 1. So now we can take our K and plug it into this equation. So we get negative 1.2, move it over, 1.2 times 10 to the negative 4th times time. So go ahead and solve for time for me. So how long does this take? Will we see this happen in our lifetime?
No.
4,221 years.
4,221 or 2?
22.
22 years. Yeah, I'm going to live forever, so I will be able to experience this. I don't know
Is
about
that your
y'all.
life story?
No, that's not my life lesson. Not that one.
That would suck. Living forever and like everyone else is dying around you.
That would kind of be bad.
But do you know
Also, if you
can
continue to
yourself
age,
by
you're just
watching
gonna
carbon
be
decay?
terrible.
It's
If
like
you didn't age, if you were like a vampire and could just like go throughout the ages, that would be kind of cool.
Well, it would be so much more cool if you had like a fun friend at least.
Well, I'm sure
yeah.
there's some other vampire friends you could make.
Yeah,
You
you
run
might
into
see.
them in different eras. Like,
Yeah,
oh,
that's
let's
what
vote.
well, Demo's
His
got
His name is
Bye.
Joe.
They would be friends
Are
with
you
Chem.
saying I am a vampire? Is that what you're saying?
I'm saying you have no friends. I'm not saying.
You can befriend each
That
other.
was,
They're
that
gonna
was
be
fun.
tough grade.
Arnold, -5. Okay,